In this video, we'll talk about graph sketching. We're going to combine all of our different techniques we've talked about so far for analyzing functions into the idea of drawing what their graph looks like just using calculus. The idea is we want to use what we know about these functions, including things like where they're increasing or decreasing, where they're concave up and concave down, as well as where these properties change, which are called transition points, namely at critical points or inflection points, and also asymptotes, because at vertical asymptotes you can also change increasing, decreasing your concavity. You get a vague idea and sketch out the graph of what this function is doing over its full range of values. So to start, we're going to look at some basic shapes of functions, and the main idea is going to be figure out the transition points, figure out what's happening in each region, sort of sketch between in the proper pattern to see what's happening here. The function is concave up and increasing. That's going to look like the right half of the x squared graph, because that's concave up and increasing. You're thinking it's heading upwards, and it's sort of heading upwards faster as you keep going to the right. For concave down and increasing, that has this sort of a shape. Right? It's going up still, but it's going up slower because I'm concave down, my derivative is decreasing. Now if I'm decreasing concave up, that's the other half of x squared. Looks something like that. Decreasing, falling down, and concave up, bending upwards. And decreasing concave down is that sort of a shape. Now what about these transition points? So I'm at a critical point, and f prime is going from positive to negative. That's going to be a maximum because I'm increasing then decreasing. So that's going to be something like, that's going to go increasing and then decreasing, giving me my maximum here at this point. If it goes from negative to positive, we're going from decreasing to increasing. That's decreasing to increasing. That's a local minimum at the point there. Now, minus to minus means I have zero derivative, but I am decreasing and then continue to decrease. That's going to be something like I'm decreasing, I hit critical point there, but I just keep decreasing afterwards. So there's a critical point here, but it's not a max or a min. And the same goes for plus to plus. I'm sort of increasing and then increasing afterwards. Now what about inflection points? Now at an inflection point, I'm changing concavity. So if it's going from plus to minus, I'm going from concave up to concave down. That's going to be something like I'm concave up, and then at this point I flip and start going concave down. You don't have to have a horizontal tangent here. It could be a sloped line as well. Something like concave up into concave down, but you're switching concavity. You're going from bending upwards to bending downwards. And for the other case, you're doing it in the opposite order. You start bending downwards, hit a point, and then switch to bending upwards afterwards. These two over here don't really matter. Those are your main shapes you're going to want to stitch together to figure out what's going on with these graphs. Basically, your point's going to be mark as many points you can in the graph that you know where they are, and what shape they're going to take, and then sort of fill in the gaps between them. Work out this example here. The function is x plus 4 over x minus 1, and we're going to analyze it using this calculus stuff. There will be a table to fill out with all this information, and then we can draw the graph of this function. So what can we tell right away from this function? Well, let's get some points out of it first. So we know that if I plug in 0, f of 0 is minus 4, because I get 4 over minus 1, and this function has a root at x equals minus 4, because that is where this function evaluates to 0. We'll also now think about asymptotes. Are there any vertical asymptotes? Yes, the denominator goes to 0 at x equals 1. And I know that by sort of drawing this out, if I'm close to 1 and less than 1, say I'm at 0, my value is negative, which means I'm going to be going this way and then come in at the top, because if I plug in something bigger than 1, then I'm positive. What about horizontal asymptotes? Well, we find those by looking at the limit as x goes to infinity of x plus 4 over x minus 1. Using our rules from before, this is 1 on both directions. So I have a horizontal asymptote at 1 on both sides. That's what we can get out of the original function. Now let's look at derivatives. Let's take the derivative of this function and see what that gives us. So f prime, this is done by the quotient rule, which we can simplify out. X minus 1 minus x minus 4 over x minus 1 squared. The x's cancel, and so I'm left with negative 5 over x minus 1 squared. Where do I have critical points? Well, this function is never 0. So the only thing where this does not exist is at x equals 1. But that's not a critical point because my function is not defined there. Therefore, this function has no critical points. Now we can look at the second derivative. So our first derivative was negative 5 over x minus 1 squared. That means our second derivative is going to be 10 over x minus 1 cubed. So I get a minus 2 that goes up top to give me a 10, and then have a minus 3 there on the bottom. This again is never 0, and only does not exist at 1, but since the function is not defined there again, it's not an inflection point. This function is relatively simple in how it behaves because there's no critical points and there's no inflection points. However, we do have to worry about that asymptote and how it interacts with things. So we can now fill in a table with all this information in it. We know there's a 0 at x equals minus 4. The y-intercept is at y equals minus 4. For the asymptotes, we have an asymptote at y equals 1 on both sides. And we have a vertical asymptote at x equals 1. We saw there were no critical points, and there's no inflection point. Now for the last things, increasing, decreasing, or concave up and concave down, we want to look at a sign chart for the first and second derivative respectively. So we have those here. And now what points do we mark? Well, normally we mark just the critical points on f prime and the inflection points on f double prime. But for this case, we don't have any of those, but we do have an asymptote. So you also have to mark asymptotes on these lines as well. So I'll have a mark here at 1 and a mark here at 1, because across asymptotes, these things can also change sign. There's our two functions. So for f prime, what do I get for signs? Well, that function's always negative. It's something over something squared, and there's a negative sign up front. So this will be a minus on both sides. For f double prime, if I plug in 0, I get a negative number, but if I plug in 2, I get a positive number. Therefore, we can say that our function is increasing never, and decreasing on the two intervals, minus infinity up to 1, and then 1 to infinity. And that our function is concave down on minus infinity up to 1, and then concave up on 1 to infinity. And so there's our filled in chart for this function. Now we're going to sketch the graph. I'm going to use a scale of 2 for this to make sure everything fits. So now I have my y-intercept at minus 4, and my root also at minus 4. I have an asymptote at x equals 1, and I have horizontal asymptotes at y equals 1 on both sides. Now we can use general shapes to start sketching the graph here. So on the left side, my function is decreasing and concave down. It has to pass through those two blue points. So it has asymptote this line here. It's going to hit this point here, keep going, decreasing concave down, and go off to infinity at the asymptote. And then I'm going to come in at the asymptote at the top because I'm now going to be concave up and decreasing, which means I have to come in from the top of the asymptote. Come in this way and just sort of asymptote out to this line with the same sort of shape over there. And that's a general picture of what this graph looks like and gives you the idea of how you can draw these sketches just using calculus information. If you have critical points, you plot those as well, and you'll have things like, you know, this is a maximum, so it's going to look something like that near the point. It's a minimum, so it'll look something like that. Inflection points, so it'll look something like this. And you can sort of put those little shapes in and then just smooth the lines between them to get an idea of what the graph looks like that you can sketch just from calculus information, getting a vague idea by hand of what these functions look like if we were to draw them out in the plane.